Today we're diving deep into the absolute lifeblood of an engine, that pressurized oil that's the only thing keeping it from tearing itself apart in literally a matter of minutes.
But first, let's kind of frame our whole investigation today with a simple question. When you look down at your dashboard, what's the one reading that matters more than any other for the immediate, right-this-second survival of your engine?
Think about it for a second. High temperature? Well, that gives you a bit of a warning, right? But a catastrophic drop in oil pressure? That can signal an engine's complete and total destruction in just a few minutes. It is the one vital sign you can absolutely never ignore.
So, why is that little red oil can on your dashboard just so incredibly critical? Well, it's because oil has a much bigger job description than most people even realize.
See, it's not just about being slippery. Oil cools parts that the engine's coolant system can't even get to. It cleans away all the nasty sludge and carbon buildup. It even acts as a hydraulic fluid for complex systems like variable valve timing. And yeah, it prevents internal rust. So what's the key to all of this? It's pressure. Pressure is the delivery mechanism that makes everything happen.
Okay, so how is this pressure actually created? How does a relatively simple pump just sitting in a pan of oil generate enough force to protect an entire engine? Let's get into it.
This right here is the single most important concept you need to grasp, and it's all rooted in basic physics. Think Pascal's law. An oil pump doesn't actually create pressure on its own, it creates flow. It's the engine's whole network of tight passages and tiny bearing clearances that restricts that flow, and that resistance is what we see on the gauge as pressure.
And what's really cool is how perfectly this simple garden hose analogy works. Your hand squeezing the hose, that's the oil pump, just providing a constant flow. Your thumb blocking the end, that's the super tight clearance inside a bearing. And that high-pressure spray that comes out, that's exactly what protects the engine's internals. It's Bernoulli's principle in action. You force the same amount of fluid through a smaller opening, and its whole character, its velocity and pressure, changes dramatically.
And this little guy is the heart of the whole system. The engine's oil pump is what we call a positive displacement type. It usually uses interlocking gears or lobes. And what that means is, for every single revolution of the engine, it's designed to move a very specific, fixed amount of oil. So it's simple. As the engine speed goes up, the flow of oil goes up right along with it.
So here's the crucial point. Just having a certain PSI reading on your dash isn't really the ultimate goal. The pressure. It's just the means to a much more important and, frankly, fascinating end.
This is the magic we've been building up to, hydrodynamic lubrication. As a crankshaft spins, it actually drags oil into that tiny gap between itself and the bearing, and this action creates an incredibly strong, high-pressure wedge of oil that physically separates the two metal surfaces. You're basically turning solid, destructive friction into smooth, beautiful, fluid friction.
And get this. The scale we're talking about here is just mind-boggling. That protective film of oil, the only thing keeping your engine from seizing solid, is often thinner than a single human hair. The level of precision required for that to work is just immense.
This quote really just says it all, doesn't it? The entire purpose of the pump, the oil passages, the pressure relief valve, it's all just to create and then sustain that microscopic film of oil, no matter what you're doing with the engine.
Now, this protective film doesn't just appear out of nowhere. Its effectiveness actually changes based on the engine's speed and load. And engineers have a way to visualize this relationship using a graph called the Strybeck curve, which shows three very distinct states or regimes of lubrication.
So let's walk through them. The second you start your engine, you're in what's called the boundary regime. This is where there's actual metal-on-metal contact, and it's where the highest wear happens. As the speed builds, you enter the mixed regime, where you've got a partial oil film starting to form. And then finally, you hit the goal, the hydrodynamic regime, where you've got a full film separating the parts, and wear drops to essentially zero.
So you're probably asking, how does an engine even survive those first few critical seconds of a cold start? Well, this is where modern oil chemistry is just amazing. Additives like ZDDP create a kind of sacrificial chemical layer on all the metal surfaces that provides protection until that hydrodynamic film can get established. It's a lifesaver. Okay, now that we get the physics, let's take a look at how engineers actually design and control this really complex hydraulic circuit. They're trying to balance both performance and efficiency, which is a neat trick.
This really shows you the evolution of the oil pump. Older designs used simple, fixed displacement pumps.
They moved a constant volume of oil for every revolution. Now, this was inefficient because at high RPMs, all that excess oil just got dumped by a simple relief valve, which basically just wasted energy. Modern engines? They use smart, computer-controlled, variable displacement pumps that adjust their output to match exactly what the engine needs, saving a surprising amount of fuel.
And for really extreme performance, engineers get even more creative. You have dry sump systems that use external tanks to stop oil from sloshing away from the pickup during hard cornering on a racetrack. Oil coolers are there to keep the viscosity stable under intense heat. Piston jets literally spray oil onto the bottom of pistons to keep them cool. Heck, even the crankshaft itself is designed to use physics to its advantage, using centrifugal force to help sling oil into the rod bearings at high speeds.
Okay, so we're armed with all this knowledge. Let's go back to that dreaded warning light. We can now actually think like an engineer to methodically figure out what might be going wrong.
Here's a fantastic rule of thumb that engine builders and mechanics have used for decades. A healthy engine should generally make about 10 psi of oil pressure for every 1,000 RPM. And this little ratio works so well because it confirms the whole system is balanced. It tells you the pump's flow is increasing correctly with engine speed, and that the engine's restrictions are tight enough to maintain that pressure.
Now, if you look at a chart like this, you can see how the pattern of the pressure readings tells a story. For example, if you only have low pressure at idle, that often points to worn bearings with too much clearance. If the pressure is low all the time across the board, could be a worn-out pump. And if the pressure builds up but then just flatlines way too low, you might have a pressure relief valve that's stuck open.
And here are the prime suspects, right? And they all tie back to that core equation we talked about. A low oil level or a clogged screen, that reduces your flow. Worn bearings or a stuck valve, that reduces your restriction. Using the wrong oil viscosity, well, that just messes with how well the film can form in the first place. Each one disrupts that critical balance.
But listen, before you start tearing an engine apart, you have to do this first. Dashboard gauges can and do fail. The only way to know the absolute truth is to bypass the car's electronics and test the pressure directly with a good old-fashioned, calibrated mechanical gauge. This is the very first step any professional technician would take, period.
And this brings us to our final thought for today. Engineers design these systems with a built-in safety margin to tolerate a certain amount of wear and tear over the years. So regular maintenance, using the right oil, changing it on time, it's not just about changing fluid. It's about preserving that engineered safety margin. So the real question is, how much of yours is left?